this is Ms. DB, and this is just a short video on how to do a couple of the problems from the 6.9 worksheet. We will be using Desmos to do some regression to find the best function that fits some polynomial models, some data. So there's an example on here that reminds us that if you find the first differences and they're constant, then you have a linear function. If you find the second differences and they're constant, then that's quadratic. We looked at that in chapter 5. And then we can continue finding differences if we have enough data. The third difference is constant mean it's a cubic, or third degree. A fourth difference is constant mean a fourth degree or quartic, and so on. So there's often not enough data to keep going past, like you can see here, with 1, 2, 3, 4, 5, 6 columns of data. We found the fourth differences, and they were constant here. So you just keep repeatedly finding the differences. Now you have to be very, very careful that when you're finding the differences, you don't make any mistakes with negative numbers or with your adding or subtracting. If there's a decrease, that's a negative number. If there's an increase, it's a positive number, and so on. So be very careful when you're finding the differences, or if you make a mistake, you'll get the wrong answer. So in number 1, 2 is just identify the degree of the polynomial. So 1, 2, 3, and 4, you're just going to be finding the differences. So 1 has it like set for you to write them out. In 3 and 4, it's a table given in this form, so you can choose how to write your differences. But I'm just going to do, I'll do number 4. So if you're going to find the first differences, right. Oh. Okay, I'm having technical difficulties here. Number 4. Let me write. Okay, I figured out my pen. So first thing you do is you check the x values and make sure they're constant, increasing or decreasing. So in number 4, the x values are increasing by +1 each time. If you don't have a pattern for the x values, then you can't go ahead and check the y values. So you have to make sure that that is true. And it is. Now we're going to do the first differences. So from 70 to 35, that's a decrease, so it's negative 35. From 35 to 15 is also a decrease. From 15 to 7 is a decrease of negative 8. From 7 to 8 is an increase of +1. And from 8 to 15 is an increase of +7. Now for the second differences, you take the differences of your first differences. So from negative 35 to negative 20, that's an increase of a positive 15. From negative 20 to negative 8, that's an increase of positive 12. From negative 8 to 1, that's an increase of, it went all the way from negative 8 to positive 1, that's an increase of 9. And from 1 to 7, that's an increase of 6. So these were all increasing. Now we look at the third differences. So from 15 to 12, that decreased by 3. 12 to 9 decreased by 3, so those are negative 3. 9 to 6 decreases by negative 3. Those are constant. They're all the same. So that means, you can look back at the table, if the third differences are constant, then that means that we have a cubic function, so it'll have a degree of 3. And that's what you have to write here, that this would be cubic. Okay, now that lets us know what kind of function we're going to have, so it'll be x cubed as the highest degree. But now we're going to use Desmos in order to find the cubic function, or the quartic function, or the quadratic function, whatever it may be, in order to fit the data. So we use the differences so that we can figure out what it's going to be close to. Now, they might not be exactly the same for real-world data, but if you can get differences that are close, like up here they found that in the third differences, that's pretty close, 746 to 739, after looking at the first differences and the second differences being very far apart. So they decided to run a cubic regression and see if that fit the data. And with r squared being really close to 1, that means that that does fit the data very well. So in number 6, you're going to find the first differences, the second differences, the third differences, the fourth differences. And when you find the differences that are very close to each other, then you'll say, oh, so maybe that's a cubic, or maybe that's fourth degree would be quartic. So once you figure that out, then we'll run regression. And in number 7, you don't have to do the differences. You can just go ahead and run regression. And in 7, we can run a couple different kinds of regression, like cubic, quartic, and see which one fits the best. So let's see if I can paste this into Desmos. So I'm copying this, and then I'm going to go up here to Desmos over here, and I'm going to make a table. And I'm going to attempt to paste my data in here. Sometimes this works, sometimes it doesn't. It doesn't look super accurate because they gave me too many columns. X1 is supposed to be I'm going to try just pasting the X's in. It did not work. Alright, so I'm just going to go ahead. You can try harder if you want, but I'm just going to go ahead and type them in. 1998 for the X, and then the price was 1,000, and so on. And you can just keep, we've used Desmos before for regression, for quadratic regression. And continue on with this. Okay, I finished putting the data in the table. Now remember that you could check the first differences, second differences, third differences, fourth, and so on, and find when you get the closest differences, and then you would know better what kind of function you want to run regression on. But I just am going to put the data in, and I'm going to use Desmos to try some different functions and see which one fits best. So my data, it looks like it's all lining up in a straight line. That's because my axes are not set very good. So click on the wrench tool to change what you see for the X and Y axis. So for the X axis, I'm going to start at 0 and go up to like 2015. For the Y axis, I'm going to start at 0 and go up to like 15,000. And then just click back on the graph to see the data. It still is not great, is it? It looks like a straight line because our years on the x-axis are so narrow. Let's just go from 1990 to like 2010. See if that looks better. That does look better. Now we can see there's some curve to this. And if I zoom out just a little bit more, I can see it starts to curve again at the top. So it doesn't really look like it's going to be quadratic, but that's the first thing I'm going to try, even though this is the chapter on polynomial. So to do quadratic, and we've done this before, you type in the first part of the equation is not y equals, but y1, and then instead of the equal sign, you use this little similar to. And then the quadratic function would be ax squared, but instead of x, you put x sub 1. So you just type a 1 after it, and we did this in chapter 5. And then it would be plus b x sub 1, and you just type the 1, and it automatically knows plus c. So this would be if it was quadratic. Now you can see it graphed it, and it's not super good. It's okay, but it doesn't really seem to show those little curves that I saw. R squared is close, 0.9809, so it's not a terrible fit to this data, and it might be reasonable. Let's try cubic. So the cubic regression would be y sub 1, and then the similar key, and then this time we'd go a x sub 1 cubed instead of squared, and then plus b x sub 1 squared, and then you just keep going, plus c x sub 1 plus d. So you stop when you get to the constant at the end. Now this one's r squared, 0.9808, is actually a little less good. So that's interesting. Let's try a quartic. That would be starting with x to the 4th power. So we just use the same format, except we are going to start with the 4th power, and then we'll go to the 3rd power, and so on until we get all the way down to a constant. Let's see, I'm at squared, and then I'd have to do d x sub 1 plus, plus e. And this one is 0.981. So these are very close to each other. This one, the last one I did, is a little bit better fit because the r squared value is the 1 instead of the 0 is slightly closer. And you could keep going if you want and try x to the 5th and see if you are able to find one that's really, really close. So I'm going to turn off the why would the x to the cubed be a, oh, it must zoom out. If you zoom out more, it must curve back up. There it goes. So when you zoom out, you can see the graphs better. So the x squared is just a quadratic. That's this one. That looks like a U or an upside down U. The cubic goes increasing, decreasing, then increasing. And the quartic actually should be like a W shape. Oh, there's the other part of the curve. Whoa, that's a crazy looking curve. So you can see that that one is, you know, has a lot to it that was not actually in our data. So you pick the function that you think fits best, and then, oh, you have to paste your graph or your link to your graph. I'm going to go ahead and do the link by just clicking on this share button. And then you get a link that you can then paste into the worksheet, remember, and then I can click on that link and see exactly what your graph looks like. I probably should have made my graph so that I could actually see the data points, because look at, they're so small. They don't even show up when I had it that way. There's my points. So let's get a new graph that shows that better. Because otherwise I'm not going to even see anything if you paste that in there. Alright, and then the polynomial function. So for the polynomial function, you have to replace this equation with the values of a, b, c, and d. I guess they don't have an e. So e must have been 0 then. So then I would write y equals, and then instead of ax to the 4th, I would write the negative 0.0000811, and so on. And then plus 0.445388x cubed plus, or negative 799.399x squared, and then plus the 47359x. So you type all that in, and that would be your function. If you were using the cubic and you got something like this times 10 to the 6th, that means that it's scientific notation, and that really has, it's a really big number. It would be this, move the decimal place to the right 6th value, so it's actually a huge number. So this is, you know, real world data is often messy. These equations aren't going to be super neat and nice, but this is a function that fits this data. Alright, so that's how you're going to do this. Again, in number 6, your differences when you stop, they're not going to be exact. They're going to be like in the example where you get something really close, you stop when they're close to each other, like a few digit numbers apart from each other. All right, that's it for today. Let me know if you have any questions. Thanks a lot.